Thank you very much for inviting me. So today I'll give you an introduction on urban fluid mechanics and the wicked problems we encounter therein. I'll explain in more detail what that entails in a bit. So I'm going to start off with just a general introduction in the area, and then I'm going to focus on some grand challenges and how we work to address these. So I'm sure everyone is familiar with this particular graph. About 10 years ago, we crossed the 50% threshold, where more people lived in urban areas than in rural areas, and the projections are that by 2050, 70% of the world population will be living in urban areas. So that means that in a little bit over 30 years, the projection is that there's 3 billion people extra living in cities. And I think it's safe to say that say the war on climate change is going to be won or lost in the city. So cities produce an enormous amount of waste. They consume between 60 and 80% of the world's energy. They produce 60% of all the greenhouse emissions. So it's the cities that we have to really focus on. So I believe they are really key in kind of producing, well, transitioning to a future that we need. And the way we do that, or the way we have to do that, is that we kind of have to transition to a high density society. Yeah, so city sprawl is a huge problem. So here, just as an example, this is the footprint of Atlanta. So in 1990, there were 2.5 million people living in Atlanta, and then this is the footprint of Barcelona, which in 1990 had slightly more inhabitants. And of course, the problem with these huge sprawling cities is that you can't build reliable transport, public transport networks, and so on. You get large distances, so you're nearly automatically locked into a high carbon future if you've got these sprawling cities. And this graph here illustrates that. So these are a large number of cities in different continents, and what you see here, it's a graph which maps out the urban space consumption versus the energy consumption used to drive around. And it's clear that if you've got little areas, you produce a lot less than if you've got big sprawling cities. So these yellow ones here are generally US cities. Right, so this is, I think, the grand challenge. So how are we going to achieve this? How are we going to achieve this massive challenge where we're going to house 3 billion people in 30 years, particularly if you realize that 60% of the cities still need to be built at this stage, and the energy consumption and the CO2 emissions associated with concrete are enormous. So if you don't plan it well, and most of this is going to take place in the developing world, you're going to get sprawling cities because people migrate to cities, there's no space, you're going to get slums, and they take enormous areas. So that's low density. So this is the big challenge that we need to tackle. And of course, we've got a big role to play in this result. So let's come to the first part of why I titled my talk Wicked Problems. So it starts with essentially a concept from urban planners. So this is by Rittel and Weiber, who in the 70s introduced this concept. So they're urban planners, and they stated that science deals with simple problems, right? They should know, they're urban planners. But if you actually, so yeah, I nearly stopped reading at this stage. Anyway, but their definition of a simple problem, it makes sense, right? So they say a simple problem is where there is a consensus about the problem definition and therefore also about its solution, right? So if you speak, for example, about an apple falling from a tree, yeah, that is a clear, and you want to know its trajectory as a function of time, then we've got a kind of clear idea of how we would solve that. F equals m times a. Unless you're in a room like this, they would say, yeah, but what do you do with the drag, and maybe the apple's rotating and so on. But these are all higher order effects, right? To first order, this is a F equals m times a simple problem, right? So then, what is a wicked problem? So there might be some subliminal messaging going on. So what is a wicked problem? So that's a problem in which there is no agreement about what the problem is. And I think in our current society we can point to at least two, Brexit being one, and the American border issue being two. So what is the problem? Is it the raping Mexicans? Or is it associated with, or is there no problem, right? That's the other argument. Or is it something in between? And if you can't agree on that, you can't agree on what the solution is either. So that's the thing about wicked problems, that once you get a societal dimension to this, it's not just about facts, it's about interpretations. There's other instances as well. Constraints are constantly changing as a function of time, such as resources that you have. And also the stakeholders are subject to change. For example, the politicians rolling in and out. So if you've been following Brexit, there's a lot of that happening over the last year. Right. So, having identified what a wicked problem is, we probably just have to just get used to the fact that we are dealing with simple problems. So let's talk about some simple problems in urban fluid mechanics. Right. Simple problem number one is that we tend to be most interested in that part of the atmospheric boundary layer that is most difficult to predict. So we live, of course, inside cities. That's the main, that's a very challenging aspect. So we're most interested in what happens, presumably, at about pedestrian level. So say 1.5 meters above the ground. What I have here is just to illustrate that is a simulation from large Eddy simulation. So this is a domain of about 600 by 600 meters. This is actually the area around Imperial College. So Imperial College is here. So there's the Natural History Museums here, Science Museum here, V&A. If you haven't been, it's well worth visiting. Of course there's traffic, and traffic emit, so we have a traffic model, and so we've got line sources which emit NOx's, and we are primarily interested in this little point here. What is the NOx concentration as a function of time? This is a little pedestrianized area, which is very nice. So lots of restaurants. So there's terraces here. People are enjoying their lunches and so on. So let's see what they're exposed to. It's a wind from the southwest, I should say. So it's a mild wind, 2.5 meters per second. Yeah, so a nice summery day. So you clearly see that in general, on the main streets, the wind kind of transports all the pollution in this direction. But at this corner, something very interesting happens. So you've got the wind coming over the buildings. You're going to get recirculation, and actually you've got a lot of transport from this main road into this area here, and you get peaks here of up to 400 micrograms per cubic meter, which is about twice the allowed hourly average, right? So you're exposed to huge spikes. So what you have here is huge intermittency, huge influence of local topology. So this is obviously a huge challenge for simulations, and also for experiments, right? So where are you gonna put your air quality probe? Are you gonna put it here, Are you going to put it on the other side? You're going to measure different things. So this is really a huge, huge issue. And of course, for us that do theory, this is a recipe for headaches. Right, so in what sense? Well, so this is of course kind of the classical view of a boundary layer, but then adapted to the city. So you've got the inertial sublayer from some way up. You've got a surface layer that's the equivalent of the inner layer. And then within this, people in urban sciences, they also have a roughness sublayer, which is the layer that's heavily influenced by the roughness of the surface. So above this line, it's the turbulence has mixed it out, arguably. And then we've got the urban canopy layer, which is the layer where we live in. So if you are out here, you might hope to get some universality, right? So the law of the wall, the Monin-Oberkopf stability theory. But once you're in here, there's very little hope that you will get universal behavior. Yeah, this is the second problem. Cities are hugely heterogeneous. So even if you might hope that you got universality in this outer layer, as the flow moves over the city, it experiences all the time a different surface, and therefore even the overlap layer will not be in an equilibrium, full stop. So this is a huge challenge. We've got green areas, we've got water, we've got cities. These towers, they're a significant fraction of the urban boundary layer. So this is not small roughness. This is, this can be as much as 30% of the urban boundary layer, or of the atmospheric boundary layer, how tall these towers are. So this is very, very challenging as well. Still simple, of course, but challenging. Problem 2 is that there is lots of disciplines that have different interests and therefore modeling needs. So on this figure you see from right to left, we go from small scales to large scales. If you're a meteorologist, all that you care about is to provide the right boundary conditions for your numerical weather predictions. So all that you're interested in is, do I get the right wall shear stress? Do I get the correct sensible and latent heat fluxes? If you're a wind engineer, you calculate, you're interested in extreme situations very often, right? So large winds, buoyancy will not be so important. And you're interested in wind loading on buildings, pedestrian comfort. Urban planners, they tend to not think about urban fluid mechanics. They probably have never thought of the word fluid mechanics in their life. But they use it all the time, right? Because they need to make practical decisions. And if you speak to urban planners, it's just amazing how many things they have to deal with, all the non-tangible stuff that we try to steer clear of. Urban microclimate, thermal comfort, also ranges a scale, a lot of scales, and then you've got, of course, the whole issue of air quality and human health. And each one of these will require different modeling technologies, and for each one of these, what they want as an answer will be different. That means that you're not going to have one model that fits all. So if you put on this graph cost of the modeling versus the amount of modeling that you have to do, right? So in cost, I mean computational power. Then, well, if you're our community, then you might dream of doing some DNS, but that's obviously restricted to very idealized situations. I think LES is in a way is a great kind of, well, I should say compromise between DNS and more heavily modeled approaches, but still it's really difficult to run. So for prediction purposes, this will not happen very quickly. This is the status quo, so runs models where you parameterize the turbulence much like you do in the oceans, and you simply run these models. They're fairly, well, they're relatively inexpensive if you compare them to LES, and they'll give you reasonably accurate answers under the circumstances. And then these are the kind of the most idealized models. So this is an example of an energy balance model, which is used by the meteorologists, for example. I'll tell you a little bit more about that. So depending on what you want, you're gonna want to use different models, right? If you need a quick answer, you're not gonna go to LES, you're not even gonna go to runs. You need something simpler. Right, another simple problem is that there is just an inherent and irreducible uncertainty in boundary conditions, for example. So this is Hong Kong. This is a picture during the night, during the day. This is one during the night. And what is clear that even if you knew well what all the materials were and so on, and you had all the roughness right, you've got solar radiation which heats the buildings, and you see that there's a massive heating going on, right? So this is going all the way from 10 to 40 centigrade. So the water is 10 degrees, but the buildings here are as high as 40 degrees, particularly the rooftops here. So they're going to drive a lot of convection, a lot of secondary motion, and this is really difficult to predict. This is during the night. So also during the night you see that the city is a lot warmer. One of the effects that is very important here is the concept of radiation trapping. So you see it here beautifully. So these roofs, they look out to the sky. So they're very cold. They're now 10 degrees because they just radiate out their energy freely. But inside the city, the radiation remains trapped. So you just get bouncing back and forth of long wave radiation. You also, of course, have sources. We're going to talk about that in a bit. And that's going to keep the city warm. Vegetation. This is, of course, highly time dependent. So the season, if you think about drag, you know, the drag difference between this and the winter is going to be enormous, obviously, but trees also have lots of other functions. They photosynthesize. For that they need water, so they're going to evaporate water. They trap heat, of course, so they soak up heat. They've got latent and sensible heat release, therefore, and these are incredibly difficult to model. And I should say that they're, of course, also they're alive. So if they're under heat stress, they just cut off. They say, oh, it's getting, I don't want to evaporate anymore. They close their stomata, and they just essentially become passive, right? So they're also, that brings another dimensions to these. Okay, this is perhaps the biggest simple problem in urban fluid mechanics, that there's these creatures around that are us. We've got anthropogenic sources. So this is a picture of Seoul. This is the amount of heating that is produced locally. So clearly that's most in downtown. It's as much as 25 to 30 watts. In cities like Moscow in the winter, it can be as much as 100 watts. So those are very sizable. Those are very sizable heat fluxes, which will modify the local climate, local circulations, and so on. And the other big one, obviously, is traffic emissions. So this is an example of Los Angeles, and that brown stuff, that is NO2. Of course, in Los Angeles, what you have is that essentially, because the air is trapped between the mountains and the Pacific, there's not a lot of exchange going on. And if you then start driving and keep driving your cars, you end up with this, right? And that's not very healthy. Right, so these are then the grand challenges. I think the main thing that we can do as a community is to identify universality classes, right? So this is a huge mess. So how do we identify what is important and what is less important? Particularly if you consider the heterogeneity in urban surfaces. So how can we reduce the parameter space, make the problem a bit more tractable? Are there universality classes? Are there certain classes of heterogeneous surfaces that we can use to show that one city is similar to another, right? Or doesn't that exist? Well, so yesterday we saw this beautiful talk by Tamai with all the drifters and so on. Wouldn't it be wonderful if we could do that in the city? Yeah, 1,000 drifters that measure all the quantities of interest. That's a grand challenge. And one of the things that is absolutely evident is that whilst in the ocean you'd like to know more, I mean, the ocean is, I think, much more instrumented than the average city. I think what we need is a ground truth numerical model for urban areas. right? So one that is able to deal with buoyancy, that understands surface energy balances, that knows about vegetation. So we're getting there on the runs level. I think the ideal is to be at an LES level. So we're working towards that. I'll say a little bit about this. Predictive tools that support decision makers in transitioning to the sustainable futures. So this ground truth model clearly is not going to give that. You need really practical tools that can give answers really fast, even if they're hand wavy, right? Is the sign right? You know, that would already be really wonderful, and Paul's going to say more about that. And then also what we're going to need is we're going to integrate field data with model data in order to obtain uncertainty estimates and improved predictions. And Catherine will say a lot more about that. All right, so what I'm going to do now is I'm going to just show you some examples of what we've been working on. I'm going to start with an example of something where you use simple modeling to actually get to very practical answers. Then I'm going to say a little bit about reducing the parameter space in the context of LES. And if I have time, I'll say a bit about our efforts to model trees. Right, so the big question here is, can green infrastructure mitigate urban heat island effects? So green roofs, like these ones, this is an example for Philadelphia. You know, they've got multiple benefits. I will only focus on their ability to reduce the urban heat island effect here. These are gaining a lot of traction. Yeah, so because they evaporate, they will cool. But how much will they cool? This is a beautiful example, a bit wacky. This is in Milan. This is called the Bosco Verticale, the vertical forest. I mean, from a wind engineering perspective, I think this is a nightmare. But still, you know, it looks amazing. And the idea here is, if you've got vegetation on the sides, it evaporates, it shades, and so on. So it will actually, and it also, you know, it's nice to look at. So it has a large influence. So we're going to look about predominantly green roofs and then a little bit about green walls. Yeah, that's housing. Yeah. Yeah. Amazing, yeah? Yeah. So I should say that this work here, it originated from a project called the Blue-Green Dream Project. And this aimed to create sustainable cities by combining blue, which is water resources, and green resources. So it was a lot about closing loops, water recycling, waste recycling. My role in here was to quantify the interactions between the city and the atmosphere. And the nice thing of this project is that it involved a lot of industrial partners, it involved urban planners, it involved architects. And I can honestly say that I've never felt as much out of my depth in my life. Which was great, because I learned a lot, because the way that planners think is completely different from the way that I think. So we wrote a little guide about this, which you can download from the link below if you're interested. So I'll just tell you about this, about the research that we did for this question about green roofs. And we wanted really kind of practical solutions. And as a fluid mechanics person, you kind of come in confident, you know, I know about boundary layers, I know about buoyancy, how difficult can it be? Well, one thing that you really can't do without in an urban area is radiation, and that really complicates matters. So you got this surface energy balance, because the principal driver is shortwave radiation. Part of it gets reflected, and then of course what happens is that your urban surfaces heat up, they start radiating out long wave radiation, that gets absorbed back in the atmosphere, part of it comes back, so you get re-radiation of long wave radiation, and then you get, on these surfaces, you get convection, so you get a sensible heat flux, you get a latent heat flux, so water evaporates, and that creates a heat flux, and then you've got also influences from the ground. They tend to be small. And these things are never in a balance. So what is the imbalance between this is going to end up either stored or released from the temperature of your building. And this is what generates the urban heat island effect. So there's a lot of information on this chart, but this is a rural area, this is a suburban area, and the big differences that you can see is that in the rural area you've got a latent heat release of 300 because there's lots of green, and that reduces to 200 in the suburban area. So you get less evaporation. Makes sense? There's less green surface. Also what you see is that the heat storage in the buildings is much larger than in the countryside. So you're going to get a memory effect. The buildings are going to be warm, and that is going to translate into different convection patterns in the night because this heat is still being released. Right, so that gives rise to the heat island effect. So this is an example from a heat wave in 2003. So this is London. This is a place in the countryside, High Wycombe. And you see that in this particular heat wave, there's an 11-degree difference between the temperatures in London and in the countryside. And of course, that's a problem because if there's a heat wave, people start dying. And particularly if it gets over 35 degrees, there's a very strong correlation. So you want to avoid this, and can green roofs help? So that's the question is. So we've tried to put ourselves in the mind of a planner, of a decision maker, and what this person might ask himself. Say I've got a certain amount of water available, maybe 40 millimeters over a certain number of months. How much can I cool my cities with this? Or say I've got a real problem with urban heat island effects. I want to reduce it by 2 degrees. How much water would I need to achieve that? So what we did is that we went for the meteorological model. So these are, as I already mentioned, these are used to provide the boundary condition for numerical weather prediction. So the way it works is that essentially you look at the buildings. This is the atmosphere here. So these are the buildings, and essentially you've got resistors which say, okay, so you've got a certain temperature here, you've got a certain temperature there. There's a certain resistance, and that's going to tell me how much flux there is. And of course, all the fluid mechanics is parameterized in that resistance. Yeah, you've got a slightly more complex coupling between the walls, the road, and the canyon itself, which then links to the atmosphere. It's a very simple model. And what you do is that you've got the buildings, the vegetation, and the impervious surfaces, and they all essentially act independently from one another. So what we did is, okay, so we need to adopt this to be able to model green roofs. So what we did, if you've got a green roof, of course, you've got a problem because you want to know how the effects from the green roof end up in the canyon. So if you only have a resistance going to the atmosphere, this is a boundary condition, it's gone, so you can't measure the effect. So we modeled the surface layer, so we introduced an extra layer. The green roof interacts with the surface layer, and the canyons interact with the surface layer, and the effect of the green roofs can find its way back into the canyons in that way. Okay, so the nice thing is you get a relatively simple system where you've got, well, 7 different quantities which you want to know in time, so temperatures of the roads, of the walls, the amount of water on the roads and on the roof, and so on. And then of course you've got an ODE system with a time-dependent forcing, right? Which is, for example, the solar radiation. Right, so to make it even simpler, we said, okay, let's just look at a steady state. So it's a situation where the sun is always shining. So we just have the daily average radiation incoming, so 480 watts per square meter, and we looked at 4 different scenarios, so temperate climate, a warm climate, and then narrow and wide streets. Right, so what did we find? Well, so we found that as you increase the green roof fraction, you get more evaporation and the temperature starts dropping. And what you also see is that not all the scenarios produce the same slope. Yeah, so it's linear, so that's nice. This function f is a really nasty function. So if you get linear behavior, that's quite exciting. If you then say, well, probably the amount of flux of the amount of green roofs is not the direct variable we need to look at. We need to know about how much energy are we is going into evaporating. So we need to look at the evaporative flux, and if you plot that against the temperature drop, sorry, I should have said this is the temperature drop in the surface layer, so the layer above. And you see you get a full collapse of all the different scenarios, which is nice because that means that the temperature drop is directly related to the amount of energy that you put into, that goes into evaporation by a constant, and that constant is 0.014 meters squared Kelvin per watt. Right, okay, so you might say, okay, what happens if you put a diurnal cycle in? Surely that must be different. So we did that, so then the surface temperature obviously becomes something which becomes a function of time. And what we find then, actually, if you average the temperatures over the entire day, yeah, so then those averages will still lie on exactly that line. So this is exactly the same value, this 0.014. So that works really well. Of course, what you're most interested in, what happens to the peaks. So these times, so they will go down further. Then you get these stars here. And it turns out that there's a really easy way to go from this dashed line to the blue solid line, which is just to take the well, essentially the ratio of how much hours are there in a day over how much sunlight there is. So we then end up that the maxima correspond to minus 0.02 Kelvin meter squared per watt. And this is interesting because there was other simulations that were performed with WRF, so with much more sophistication, which produced a very, very similar value. So sometimes simple models produce pretty good outcomes. And of course, the nice thing about having simple models is that you can actually do some analysis. So it's only a 7 variable ODE. So what you can do, because you've got the linear behavior, you perform a Taylor series expansion, and then you say, okay, so we've got a base, we've got a kind of a base state, and we're going to perturb that. And we're just going to perturb the amount of water that we're putting into the soil, and then you can get an analytic expression for E. So you can see what you have to do to manipulate it. So that's nice. Of course, from answering our original question, this is pretty pathetic, right? If you want to achieve, say, 1 degree of reduction, you're going to have to evaporate about 2 millimeters of water a day, which is enormous, right? In the summers, you don't have a lot of water available. So on a high level, this tells you that if you're interested in reducing the urban heat island effect, don't think of green roofs. I mean, there's lots of other reasons why you should think of green roofs. The fact that you can harvest water, the fact that that you get some local advantages, but this is not the one. What is much better then, of course, because we live in the canyons, is to look at green walls. So we had a master's student looking at that. So he did exactly the same trick, but now with the walls. And as you can imagine, the walls, because you cool where you want it, they work a lot better. So these are slightly different units. So this is the amount of cubic meter you evaporate per day per hectare. But if you take 20 as an answer, then this would cool about, well, not even 1 degree for when you use a green roof. But if you put the green walls inside the canyon, you can get as much as 3 or even 4 degrees cooling. Yeah, so this is a much better way if you want to keep your streets cool. Right. The next topic essentially is associated with large eddy simulation and reducing the parameter space, right? So one of the big trouble when you deal with this is that you've got this diurnal cycle, right? And when you are thinking about wind engineering, you're thinking about extreme cases. Yes, so you want to know what happens when there's a lot of wind. But when you're interested in microclimates, you're interested in air quality, very often you're interested in the situations when there is little wind. So that means that essentially you will have a huge variation over the day, with what you get. So what we were after is, wouldn't it be great if we can design simulations where you can stop time, so that you can just stop the state of the atmosphere, that you don't need to deal with all the slow transients, so that you can do systematic analyses of what happens when you've got a stable stratification, what happens if you've got a convective mixed layer. So that's what we were after in this bit of work. So the code we use is derived from the Dutch atmospheric large eddy simulation model. So this is an atmospheric code. It's been in development for 20 years. So the nice thing about it is that because it's derived from an atmospheric code, it's got the full wet thermodynamics in it. And of course, these are really important for these low wind situations. Convection is going to matter, and evaporation is going to matter. Pretty standard solution for the building. So we used an immersed boundary method, and we use wall functions to deal with the last, say, meter or half a meter. So I personally believe that LES is the ideal candidate to provide this ground truth model, but it has some problems. One of them being is that boundary conditions are really difficult, because LES is eddy resolving. If you've got inflow boundary conditions, usually what you have from atmospheric measurements is just means and variances, and the same for temperature. So you need to somewhat, on your inflow, you need to reconstruct a turbulent inflow velocity profile from data. By definition, you're not going to know how to do that, right? So there's methods, and they work, but the problem is that you're not feeding real turbulence into your domain. Now you can argue that because of the roughness, it's going to sort itself out, but you can get real, particularly if you look at stably stratified situations, you're going to get cases where there's real inequilibrium in this system. So what we try to do is the other method, which is to use periodic boundary conditions, where essentially I always call it a Pac-Man domain. So getting a bit outdated, that analogy, but I think in this audience it will work. With my students it doesn't work anymore. The nice thing about it is, because this recirculates, whatever you get is real turbulence. It's quasi-homogeneous, which is a dream for modelers like myself, of course, because all the statistics become a lot easier. You get more symmetries. Well, you can't simulate developing flows, but the problem I want to tackle here is, how do you simulate non-neutral situations? Because that is not possible with LES, as I will outline. So what we want to do is to freeze time. So we've got a certain time of the day, we've got a certain velocity profile, we've got a certain buoyancy profile. We freeze time, and how do we simulate that in a LES with periodic boundary conditions? Well, so let's just look at the let's look at the homogeneous situation. So we've got horizontal momentum, there's some forcing, usually by pressure, and then we've got our temperature equation, or our buoyancy equation, and we're going to integrate those over the entire atmospheric boundary layer. So then you're going to get an average velocity in the boundary layer. You're going to get a growth of the boundary layer by entrainment processes, so that's very important. You're going to get differences between the shear stress at the wall and at the top. Of course, the top is negligible, and then you're going to get your integrated forcing. And the same is going to happen when you look at buoyancy. So you're going to get a temperature which will change in time, and you're going to get your boundary layer depth. And then here you get the differential in the fluxes. So when you looking at steady states, the question is, how do you ensure that U hat, H, and theta hat are all constant? Right? So we want this to be constant. So you see there's an easy fix. We just set H, we just cap H to be some level so that it can't change. Very often it's not even to the top, it's just it's at 200 meters above. That's going to get rid of this. We're going to get a balance between the shear and the forcing, so we're going to get a nice steady state. So those are all the neutral simulations that are out there in the literature. Now for temperature it's much more difficult. So if you want this one to be zero, and you're going to cap it as well, you see you get an imbalance here. So delta phi is 0. So you're going to be pumping heat in, so you will have to have a transient, right? So So this is the problem. There's no forcing on this side. So the way we're going to solve it is to put a forcing in the buoyancy profile. And the question is, of course, what forcing should you choose? Well, if you look in the literature, there's many that you can do. So I've already discussed the capped solution. What you can do is to choose boundary conditions, so just change the boundary conditions on your atmosphere, right? So you've got an influx of 60 watts. Just make the outflux also 60 watts, and then you're going to get a steady state. The question is, does it influence your turbulence? Because that's very important for air quality and so on. What you can also do is you can do some nudging. So we saw an example of that yesterday, where you just nudge profiles back to their preferred state. We can cap it and use volumetric sources and sinks. Okay? So we're just going to take out heat evenly, or maybe not evenly, across the depth. And what we are going to look here at is a solution where we don't cap anything, and we're going to use volumetric sources and sinks with subsidence term. Yeah, so we're going to have a sink and a source with a subsidence term, and that's not capped. And it sounds crazy, but it's not quite so crazy, because there's two main mechanisms that we essentially allude to and that we hijack, because of course we're trying to fix something numerically. The first one is subsidence, the fact that in high pressure regions you get a very mild downflow. This is very clear here in this high pressure region. So this air is flowing down, and that's why you don't have any clouds in this area. So the way you model that is to just have a very mild subsidence velocity going down. So this is essentially an advection term. And then we've got the radiative forcing, which is the divergence of the radiative heat flux. So at different levels of the atmosphere, you get different absorption and re-radiation of latent heat, and that's going to give a net heating at a certain point. So we're going to hijack these two mechanisms. Now the main thing we need to determine is WS. And what you can do is that you can allude to principles in fluid mechanics. And those people who know me probably know me best for my work on entrainment. So we did some work on small scale entrainment. So this was for a temporal jet. And here we were interested in the small scale behavior. So this is the entropy isosurface, and we're interested in what happens across this turbulent, non-turbulent interface. And the way we queried that was to just look at lots of different thresholds of entropy and just see what the propagation velocity was. And what we wanted to do is to link the small scale entrainment, so the microstructure of the turbulence, to the macrostructure. Okay, so how did we do that? Well, so essentially, if you've got an isolevel, you just look at an isolevel, then that by definition satisfies that if you're on that isolevel, your concentration doesn't change. And then this V here is the boundary velocity. So you can rewrite that in terms of a material derivative, and then you can get an expression for the normal velocity. So how quickly does this interface move? Yeah, so that's 1 over grad chi absolute times the material derivative of chi itself. And what you can do is essentially, so this is something which is local, this is something that you'd use in DNS, but you can use the same method on these averages. So what you do is that you say, essentially, we've got our temperature isosurfaces which are moving in time. So if I want to know how quickly they move, what I need to do is to just evaluate this term, and that turns out to be 1 over the temperature gradient times the divergence of the buoyancy flux, or the temperature flux. Right, and then essentially what you do, you find the velocity of temperature isosurfaces. So if this velocity is much smaller than the typical velocity of the turbulence, then you choose it, right? So then it won't affect the turbulence statistics. If you've got no gradients, like you would have in a convective boundary layer, you'll set it to 0, and otherwise you set it to a maximum value. Whatever you can't use, whatever you can't correct for in this expression, you put in this volumetric sink. Right, so we then look at a number of different simulations. We look at a convective, at a stable entrainment. We choose one particular time at which we want to freeze it. And what essentially happens is that for the convective case, that's by the way the easy case, you get, well, zero velocity except near the interface, and you get a volumetric sink. And for the stable situations, what you're going to get is essentially non-zero subsidence velocity throughout, and locations where you also have to correct with a volumetric sink. So does it work? Yes, it does. So if we freeze time, the red line is the transient, and this is our steady state. So this is for the stable boundary layer. That's the difficult case, and it also works for the convective case. So we believe that this is one of these examples of reducing the parameter space. So now essentially what you can do is, if you've got an air quality study, you can just work with a non-neutral stratification and see how that affects air quality. We believe this is a very strong effect. I'll just spend the last few minutes talking about vegetation. So the problem here, I've already outlined what trees do. So we want to develop a really simple model. So this is this quest for kind of a ground truth model. So far you can have that in this area, because there's always going to be heavy modeling involved. And the advantage with that, of the challenge with LES, is that you can't resolve the tree, but you're also at this uncomfortable zone where you can't parameterize it, right? So this is also what you encounter in the atmosphere and in the ocean. As the models get better and your resolutions, they become smaller or higher and higher, you're going to resolve processes, and that means that you're going to end up in a gray zone where you resolve part of the processes and you don't resolve another part. So that's the aim here. So we've got a way to do that. So what we're trying to do is to provide a minimal model that that does this. So we've got a standard parameterization for drag. So we just use it as a porous material. We've got some aerial deposition in here. The main thing is, what do you do with the energy balance? That's really challenging. I don't have time to go in that here, but what is crucial about it is that you determine the storage. So you start from the incoming radiation, and essentially the sensible and latent heat flux you only back out once you have all the other sinks and sources. So that will give you something where you've got the trees, you've got volumetric sources which tell you this much is evaporating here, this much is evaporating there, the same for sensible heating, and so on, and you're going to get a modulated incoming flux at the bottom, right? So we're assuming that the sun is going vertical. Right, I'm going to skip through all these. I'm just going to show some results. So we just look at idealized one-dimensional canyons, and then we look at the difference between trees and no trees, and we're going to look at convective and not convective. I'm going to skip the temperature. These are the, I think, some interesting things. So often it's also said trees are good for air quality. Well, that's not evidence at all, because they block, right? They also block the transport. So this is what happens if you've got no trees and trees. You see it here clearly. You get less circulation inside the canyons. What is interesting is the difference between a neutral and a convective case. And please, these are not final results. I think this is a little bit too strong what we see here. But the convection essentially creates a nearly uniform velocity profile, so you're going to get very violent exchange across this boundary. You see also that you're going to get a very strong recirculation as a result. And the trees, again, what they do is that they dampen this effect. So this is what it does for the concentration, right? So this is if you don't have trees, and this is if you do have trees. So you see there's not too much of a difference between this, but there is a huge difference between whether you have a neutral state or a convective state. So I feel this is a really important thing to start looking at, particularly at these, if you are interested in air quality. Convection matters a lot. Right, so just to wrap up, so there's an urgent need for improved understanding of urban flows and microclimate. Um, we really need a range of models. There's not going to be one model that fits all. So we need simple operational models that give us quick results that decision makers can use. We need models that we can use to really kind of serve as parameterizations for coarser models. This is, of course, a picture that Colm also showed. I think this is also very suitable for urban fluid mechanics. If this transition to sustainable, resilient cities is the elephant, and every one of us, and this now also includes urban planners, architects, politicians, financial institutions, looks at this in a different way. And we kind of have to kind of figure out altogether, without seeing the entire elephant, that it is an elephant. And this explains the title. So I hope to have conveyed that urban fluid mechanics has some quite wicked problems. And if I was really cool, I could do the flicking with my finger now. It's for those who know that, but I can't, so I need my nephews to teach me that. Right. So these are the people that I'd like to acknowledge. So my PhD students, my collaborators within Imperial, my collaborators at École Centrale in Lyon. I've benefited hugely from a special interest group on urban fluid mechanics that we've had over the last 2 years. So we've got meetings every 6 months. So Paul is on the steering committee. And also the Imperial College and Archer HPC facilities. Thank you.
So that was a really good talk. I have a question about, you said a grand challenge is that we need more data in cities.
Yeah.
And I was wondering how you felt about the Google streetcars now that they're instrumenting with air quality sensors and getting like millions of data points. Is that, how useful is that?
Well, yeah, so there's lots of these things that are happening at the moment. So Google is one. There's one really crazy idea as well, where you've got lots of pigeons that are flying around with air quality sensors. So in general, so we're in a really exciting time in that these sensors are becoming more and more available, and you know, you can even have air quality things on your phone. And there is I think a real opportunity here to use that data and integrate it with our models, right? It's generally low fidelity, because it's not the same as having a high precision instrument which is highly calibrated in a place. But if you can understand what the uncertainties are, they will hugely improve our understanding of what the urban environment behaves like.
Yep. I'm involved with an organisation that's planning to build a 50-storey building in Melbourne. And we're just getting to the stage of trying to make it as an ideal building as possible. And the sort of things we have in mind at the moment are minimising energy consumption.
Yep.
And recycling water as much as possible.
Yep.
So making it green is something that you have to think about. But obviously these other concerns I think are really quite important, and how we can. You haven't mentioned things like energy consumption, but if you minimise energy consumption, that removes the amount of heat that's going in, effectively the amount of heat that goes into the building.
Absolutely. Yeah. So yeah, I agree. I haven't mentioned that on purpose. I mean, Paul will say a lot more about energy consumption in buildings this afternoon. So I've stayed on the outside, but I completely agree that these are the ways to do it.
Yes.
Yeah.
Yeah. Thank you.
Thank you for the talk. You didn't mention too much the problem of multi-phase flows, so solid particle pollution that you might encounter.
Yeah. That's true. It's there's a lot unknown there as well. I'm sure Paul will say more about that as well. So essentially, I didn't touch air quality, right? So one of the big challenges is that even if you know what car you drive, the way you drive it, the history of the particular car will matter hugely in the kind of aerosols and particulate matter that you produce. So we don't know much about that. We don't know much about what trees do, how much of these aerosols ends up in trees, how much end up in the surfaces, and so on. So I agree. This is another grand challenge.
Thank you for the talk. That was very interesting. I wanted to ask about your first model where you see the linear behavior.
Yeah.
Do you know why you see that? Because we've often seen if you have a very complex problem, it shows a linear behavior. It means that one process really dominates
Yeah.
the prediction. Is that what you found?
Yeah. So what we found is that the main thing that you want to get right, because you end up, if you do this, where are we? Yeah, so if you do this Taylor series expansion, you get this Jacobian is going to be 7 by 7, and the way we end up with this formulation is that we essentially we only look at the interaction of water and temperature between the green roof and the surface layer, and once we have that's the dominant process, then essentially we can predict this. Yeah, so that's the main process that's going on here.
Hi, at the beginning you kind of mentioned the objective of having universality classes, and in generalizing stereotypes, the picture you showed about population density and energy consumption, there was like North American, very sprawling, European, built by medieval monks, and then Asian, very, very high population densities in the corner. Can the three different ones have anything to say to each other? You know, the issues in Hong Kong are surely completely different from the issues in Los Angeles.
Well, that's absolutely true. I mean, one of the things that you find also when you think about blue-green solutions and so on, is that what you do in a climate like London or Paris is completely different than you would do in Milan or in South Africa or in Asia. It hugely depends on the humidity, how much rainfall you have, and all these kind of things. So I think what is needed is that there's so many of these variables, so it's essentially an infinite dimensional parameter space, and can we cluster them even in crude classes? I think there's a lot of work to be done there.
Actually, if I could just piggyback on that for a second. There's been a lot of work over the past decade or so from people like Jeff West and Luis Betancourt on scaling laws in cities. Is any of that useful for this, or is that a totally different topic?
Well, no. So it's certainly useful. I mean, there's many different, as I said, there's so many different ways of looking at the city, and we just need to look at these in an individual matter, right? So the things that I've been thinking about most is, you know, how do you translate some say generic roughness, perhaps even a fractal type roughness, to specific wall shear stresses, sensible heat fluxes that you might encounter locally, right? So those were the universality classes that I think about. If you go to the larger scales, you know, there you will find different ones. So this needs to happen all across the scale. So yeah.
I think one more question here, so we can keep on time.
So I'm wondering how much, given the challenge of the absence of data, the reality is there's a significant amount of data in the urban canopies about energy and heat and fluxes, but it's sitting within each building. So if you think about essentially all buildings to some degree are smart buildings today, or most buildings, certainly in the developed world. So the equivalent would be in the residential space. We have smart meter data for electricity now on probably half the homes worldwide in the developed world, but that data is locked up by the owners, usually the utility, and there's a huge sort of social behavioral science question about how do we unlock that data security. Every building, of course, is monitoring at pretty good accuracy what surface fluxes are, on-off systems. We know what's happening, but that data is not available to you yet. Is the community talking about trying to figure out protocols to make that data available, and would that data be helpful?
Well, that data would be enormously helpful, and actually within the Urban Fluids Special Interest Group, one of the things that we've been setting up is a data portal where we start grouping data, the data that is available, and we're talking to consultants and industries and so on they're, as you say, they're very reluctant to share. So very often, if you've got a designer, they're not very keen to share how well or not so well their building performs. But this is absolutely crucial if we want to make progress. So we are in those conversations, but they are slow.
Well, thanks very much.